Let us now talk about independent events. So two events A and B are said to be independent if probability of A intersection B is probability of A times probability of B. Notice that this has nothing to do with the English word independence. This is strictly a mathematical definition. Now the term independent comes from the fact that probability of A given B is probability of A intersection B over probability of B. So this is the definition of conditional probability. So instead of probability of A intersection B, if you write this as probability of A times probability of B, then you can cancel probability of B out, you get probability of A. So that means if you condition A on event B, you still get probability of A. So having this B here did not make any difference to the probability of A, and that is why you say A and B are independent, because you can use this definition right here to get probability of A. So that is the origin of the word independent in probability. Now very important, the independence does not imply that A intersection B is a null set. So the word independence in English would mean that, say, two sets A and B are disjoint. They have nothing to do with each other. Now in that case, A intersection B would just be a null set, and that would mean probability of A intersection B is 0. And in that case, probability of A given B is also 0, because you will say A given B is probability of A intersection B divided by probability of B, and that would give you 0. And that does not help you at all, because now you just have gotten a 0 here. So it does not help you in any kind of conditioning. So therefore, beware of the trap that the word independence in English is not the same as independence in probability. So do not make this fallacy of A intersection B being independent or disjoint from each other in the word which means in English. So you focus on this part here. Probability of A intersection B is probability of A times probability of B. Now let us do an example. So consider two coin toss. So the sample space is head head, head tail, tail head, tail tail. So A is the event that you have head head, then head and tail. B is the event you have head head, but then you have first coin as a tail and second as a head. So A intersection B is just head head. This is the common element. So A intersection B is head head. So probability of A intersection B, this is equal to 1 by 4, because you just have one outcome out of these 4 outcomes. This is equal to probability of A, there are 2 outcomes out of 4 here, so it is 2 by 4, times probability of B, again it has 2 outcomes out of 4, so this will be 2 by 4, and this will become again 1 by 4, because this 2 times 2 is 4. So this is talking about independence of events. So you can say A and B are independent events, because probability of A intersection B is probability of A times probability of B. Now you can extend this definition to n events. So for that you will have to have probability of E1 intersection E2 intersection E3 and so on to intersection En will be equal to probability of E1 times probability of E2 all the way to probability of En. Also, any two of these events have to be independent. So probability of Ei intersection Ej is equal to probability of Ei times probability of Ej. So for any two events I and j, you have to have this. For example, probability of E1 intersection E2 has to be probability of E1 times probability of E2. and you have to have probability of E1 intersection En has to be equal to probability of E1 times probability of En, and so on. So in case this holds but this condition is violated, then the events are not considered independent. So let us see an example. So say you draw a card from a pack of 4 cards which are numbered 1, 2, 3, 4. So your sample space is 1, 2, 3, 4. You could draw any of these 4 cards. So say A is the event, you could draw card 1 or card 2. B is the event, you could draw card 1 or card 3. C is the event, you could draw card 1 or card 4. So probability of A intersection B. So probability of A intersection B, this is just A intersection B is just 1. So this is probability of 1, which is just 1 by 4 because 1 is just one outcome out of 4. So probability of A is, there are 2 elements here, so it is 2 by 4, and probability of B is also 2 by 4 because there are 2 elements here. So you multiply these two, you also get 1 by 4. So this equality holds. A intersection C again is 1, so probability of 1 would be 1 by 4. Probability of A is 2 by 4. Probability of C is again 2 by 4. There are 2 elements here, and there are 4 elements in the entire sample space. So probability of C is 2 by 4. So again you get 2 by 4 times 2 by 4 is 1 by 4. Similarly, C intersection B, this is again 1. Probability of 1 is again 1 by 4. But probability of C is 2 by 4. Probability of B is 2 by 4. You multiply them, you still get 1 by 4. So these 3 events are independent. A is independent from B, A is independent from C, C is independent from B, but they are not mutually independent. So see, probability of A intersection B intersection C. So A intersection B intersection C, all of them have one common. So A intersection B intersection C is just 1. Probability of 1 is 1 by 4 because 1 is just one out of these 4 elements. Whereas probability of A is 2 by 4, probability of B is 2 by 4, probability of C is 2 by 4. You multiply them and you get 1 by 8, which is not equal to 1 by 4. So even though A is independent from B, B and C are independent, A and C are independent, A, B and C are not mutually independent. So therefore we say both of these conditions have to be satisfied for the events to be independent.